Now, by this point in organic chemistry, you should be very adept at identifying nucleophiles and electrophiles, and I know you are. And now we're going to talk about nucleophilic addition reactions to carbonyl groups. And why are carbonyl groups electrophilic? Well, there's two reasons. Number one reason why a carbonyl group is electrophilic, I like to think of the induction first, right? I always think, okay, well, oxygen's more electronegative than carbon, and so there's going to be a dipole going in this direction, which is going to render my carbon partially positive. And so a nucleophile can come in and attack like this. You can also look at it from the point of view of resonance, and you can see here that somebody has put in the two resonance forms of this ketone. So this is acetone, but you can see how one of the resonance contributors has a positive charge, has a carbocation right here. And so we see whether we look at it from the point of view of resonance or induction, the carbonyl carbon is electrophilic, and therefore it's going to be susceptible to nucleophilic attack. And so what happens when the carbonyl undergoes a nucleophilic attack, we go from an sp2 hybridized carbon, which is trigonal planar. Now again, I know you know all this, but you see that this carbon that I'm highlighting in red, it's sp2 hybridized, right? It's attached to 1, 2, 3 substituents. So 3 regions of electron density, sp2 hybridization, your nucleophile comes in and attacks. And the thing is that the nucleophile could attack from this top face as is drawn here, or it could come and attack from the underside. It's indiscriminate. Why? Because the molecular geometry is trigonal planar. It's flat. That's why they put this blue square here to show you that it's completely flat. So we go from something that's trigonal planar to, after our nucleophilic attack, having a tetrahedral center that is sp3 hybridized. So we're changing the molecular geometry after nucleophilic attack on our carbonyl carbon. And so when it comes to the reactivity of a carbonyl to a nucleophile, it turns out that aldehydes are generally more reactive towards nucleophiles than ketones. Now, why would that be? There's two reasons. Number one, I bet you could guess right away, is sterics, okay? If you look at the ketone, right, the carbonyl is flanked by 2 R groups, which might prevent, your nucleophile from being able to come in between the two carbon-based groups like this. But in an aldehyde, yeah, on one side we have an R group, but on the other side we have a measly hydrogen, right, which is the smallest element on the periodic table, which makes it easier for our nucleophile to come in like this and do our nucleophilic attack. So reason number one is based off of sterics, but reason number two is based off of an electronic effect. And hopefully you remember that R groups are electron donating, right? And so on a ketone, we have 2 electron donating R groups, or alkyl groups. You can see the dipoles here, and those diminish the partial positive charge, or they stabilize it, rendering this carbonyl less susceptible to nucleophilic attack. Whereas on an aldehyde, you only have 1 R group that's donating some electron density in there and stabilizing this positive charge, and therefore it's going to have a greater partial positive charge and therefore be more prone to nucleophilic attack. Now, it turns out that some nucleophiles require acidic conditions, and we're going to see plenty of them, whereas others require basic conditions. And an example of a nucleophile that requires basic conditions would be a Grignard reagent, right? The Grignard reaction requires basic conditions. You would remember that if you took a Grignard, like let's say you had methyl magnesium bromide, okay? If you had that in aqueous acid, right? If you put this even in the presence of water, okay, which is a very weak acid, it's just going to protonate, and you're going to end up with methane, which is a gas, and it's just going to go up the smokestack, so to speak. And so that's why we have to be very sure that we don't have any acid in our reaction flask when we're doing a Grignard reaction, and meaning even water. So you can see here we have our methyl magnesium bromide, our methyl Grignard. And so if I just write methyl with a negative charge, right, it's our nucleophile. We've seen this mechanism before in the alcohols chapter. Nucleophilic attack. Like this, we form our tetrahedral intermediate. And in the second step, it says H2O, but remember, it could be H3O+, and that's what's going to do the proton transfer and add this proton to our alkoxide. And so generally, a strong nucleophile is going to mean that the reaction is under basic conditions. And so you can see the generic mechanism for nucleophilic attack on a carbonyl under basic conditions. It's always the same thing. The first step is going to be the nucleophilic attack. So maybe I could use my highlighter for that. Nucleophilic attack, right? We form our tetrahedral intermediate. Then we do a proton transfer, and we get our alcohol in this case. However, under acidic conditions, we're going to reverse those steps. The first step is going to be a proton transfer, okay? And I'm going to mention this several times, but the reason why we have to do a proton transfer under acidic conditions is because I want you to remember this. A ketone is a good electrophile. So we'll put here good electrophile. However, when we protonate the oxygen, okay, when you do a proton transfer on this oxygen, now all of a sudden you have what we call an oxonium ion. So this is called an oxonium. Let me get a red pen here. Oxonium. And the oxonium ion, make sure you remember this. It is an excellent electrophile. Very powerful electrophile. Much more powerful than this, right? Why? Because it's got a positive charge right on it. This thing is starving for electrons. And so whenever we're dealing with weak nucleophiles like water or an alcohol, we always have to do this proton transfer first to render the carbonyl very electrophilic, and then our nucleophile can come in and attack. And so this is what I was just saying, okay? So I'm going to write it down again. I said I would repeat myself. We'll say this is a good electrophile, right? There's nothing wrong with just a carbonyl compound, a ketone, being a good electrophile. But once you protonate it and make your oxonium ion, now it is a very powerful electrophile, excellent electrophile, right? He even wrote here, better electrophile, very powerful, excellent. Okay, so remember that. Once you protonate, now you've got something that's extremely electrophilic, and so it's going to be able to react with weak nucleophiles. What kind of weak nucleophiles? Things like water. Water's a weak nucleophile. What about an alcohol? An alcohol. Alcohols are also weak nucleophiles. Now, when a nucleophile attacks a carbonyl group, whether it lies to the side of the tetrahedral, compound here, or the carbonyl compound, that's going to depend on the ability of the nucleophile to act as a leaving group. So here you can see that we have an equilibrium between a ketone and HCl, and then this tetrahedral compound here results after the nucleophilic attack. And chloride is an excellent leaving group, right? Very, very good leaving group. And so since chloride is the nucleophile, but it's also a great leaving group, it turns out that in this case, the equilibrium is actually going to it's actually going to lie more to the side of the ketone. So these equilibrium errors that I've drawn in blue are more accurate than these ones here. And so what we're going to do for the remainder of this chapter is just going to be a systematic approach to looking at all these different nucleophiles here. We're going to start with oxygen nucleophiles. It could be a water. It could be an alcohol, right? Those are weak nucleophiles. We could also look at a diol, okay? We're also going to look at sulfur nucleophiles. So we could have H2S, hydrogen sulfide, or we could have a dithiol like this. Those are good nucleophiles, better nucleophiles than alcohol and water. Then we have nitrogen nucleophiles. So we're going to look at primary amines. So this amine here, this would be a primary amine, and then we're going to look at secondary amines. Tertiary amines don't make good nitrogen nucleophiles, and that's because they don't possess a proton on the nitrogen. Then we're going to look at hydrogen nucleophiles like lithium aluminum hydride, sodium borohydride, and then carbon nucleophiles. This is an interesting section. We're going to review some of our Grignard chemistry. We're going to look at cyanide as a nucleophile, and then we're going to touch on this reaction here. This is, if you're like, what is that thing there? That's what we call a Wittig reagent. So this is the Wittig reaction that we're going to study later on. And Wittig won a Nobel Prize for this reagent and the chemistry that accompanies it. So very important chemistry.